internal learning. We have Yossi, who is going to talk about his really fascinating work on bats. Jonathan is going to give us a really...
Yeah, so let's stick to the schedule, and I will do just a brief introduction. So it's really a pleasure to have here Professor Michal Irani from the Weizmann Institute of Science in Israel. And thank you for joining, even though it's, I think, pretty late here already in Israel. So Michal did her PhD at the Hebrew University of Jerusalem, then was at some time at Princeton. And she's very well known, probably one of the most important figures in computer vision in Israel, and not only. And I remember when I was a student and was also working in this field or adjacent fields, Michal already was a legend, at least in the sense that I think she never had any paper rejected from CVPR or ICT.
I did.
But at least that was the saying. So that she managed to publish without any rejection in these conferences, which are really cutthroat, and the acceptance rate is very low. So, and today she will be talking about her recent work on how to do deep learning with zero-shot deep learning.
So after such an introduction, I think I should probably stop here, because from here it can only go downhill.
Oh, it will go up.
Anyway, so thanks for the introduction. So I'm not going to talk about communication, not human communication and not non-human communication. So how is this relevant to the workshop, and what is this all about? What I'd like to tell you is how we can learn from very, very little data, often no data at all, no prior examples, simply by exploiting the internal structure of the test data itself. And since I come from computer vision, I'm going to show this on images, but I believe this goes well beyond computer vision. I believe it applies to other domains as well as other structured signals, and hopefully also to non-human signals. What is deep internal learning? The idea is how we can train a deep network in a totally unsupervised way by with no prior examples whatsoever, by training on a single image, the test image alone, okay? And we do this by training on examples extracted from the test image. We train the network using these. Now, why is this interesting? Well, we're all used to what I call external learning. That is to say, we train a network on lots of examples, external examples that are given to us prior to the test data. And we train the network for days or weeks. And then once it's trained, we apply it to new test data we never saw before. And of course, this has been tremendously successful. But what happens if we don't have enough training data? Or what happens if the statistics of our test data is very different than that of the training data? It turns out that in those cases, deep learning does quite poorly. And what I'd like to show is how we can often resolve these problems by replacing external learning with internal learning. And as I'll show you, this has a wide range of applications in computer vision, including super resolution, spatial super resolution in images, temporal super resolution in video, image dehazing, image segmentation, transparency separation, retargeting, all without ever having seen any prior examples. And I'll also show our new work on mind reading, how we can decode brain activity, fMRI data with very little fMRI data, and reconstruct the images that the person saw. And you'll also see that there we train on the test datum as well, which is in this case fMRI data. Also, the test fMRI data. So let's start. So how can we learn? How can we train on a single image? Well, let's look at this. A single image has lots of recurrence inside it. The recurrence occurs both within the scale, the original scale of the image, as well as across different scales of the image. When I say that there's recurrence within scale, I mean that if you see a small patch once inside the image, you'll almost surely see it many more times in the image. Now, here I'm showing relatively large patches for visualization purposes, but in practice, I'm talking about much smaller patches, 5 pixels by 5 pixels or 7 by 7. And this has been used by us and by others for lots of different applications in computer vision, including image completion, image denoising like non-local means, BM3D, etc., visual summarization, and many other applications. Less commonly known, but also very useful, is the recurrence of information across scales in the image. That is to say, if I take the image and scale it down, then patches in the original scale will almost surely appear as is in downscaled version of the image without scaling down the patch. which means the little small patterns in the original image appear in multiple sizes inside the image. And again, I'm talking about much smaller patches than what you see here. And this property has been used by us and by others for many applications, including fractal image compression, super resolution from a single image, blind deblurring, blind dehazing, and many more. Now you can say this looks like a very contrived image, and does this really go beyond images with such repetitive structure? And the answer is yes. If you go to small patches, 5 by 5, 7 by 7, this property is true for almost any patch in almost any natural image. For example, if you look at this image with no clear repetitive structure, then look at this patch over here, this edge patch. It repeats many more times along this window seal. Or similarly, across scales, this edge patch recurs again here without scaling down the patch. Or this corner patch. Again, I'm showing large patches. I'm talking about much smaller ones. So you can say, okay, repetitive structure, edges, corners. What happens if I take unstructured information like this? Well, let's zoom in and see this. And you can see that the information is quite repetitive across scales. You see the same statistical structures. And we empirically verified that this very strong fractal-like property is very, very strong in natural images. And you can find this in our 2009 paper. We empirically verified this for hundreds of natural images, indoor, outdoor, man-made, natural. And it turns out that this is true for almost any patch in almost any image. So as I said, this gave rise to lots of applications over the past decade or two. And the real nice thing about it, it's totally unsupervised. I don't need any external examples. All I need is the single test image, and I can solve Ilpo's problem simply by exploiting this strong prior, by maximizing the recurrence of information within and across scales of the image, the recurrence of patches. The bad news is that in the last few years, it has been completely outperformed by deep learning methods. So this is very depressing. And initially I was totally depressed for a year or two. And then I said, okay, if you can't beat them, join them. But on one hand, it's very unsatisfying. On one hand, we have this deep learning, which is amazingly successful, but is extremely data hungry. And we don't really understand what the network learns. On the other hand, we have this very strong internal redundancy, which we understand it. It's totally unsupervised. We don't need any additional examples, but it doesn't perform well as deep learning. And for a long time, I was asking myself, is there any way to combine the power of these two very complementary approaches? And luckily, 3 years ago, my brilliant PhD student, Asaf Shochel, came up with the idea of doing deep internal learning. That is to say, let's train an image-specific CNN. CNN, for those who don't know, is a convolutional neural network. Let's train an image-specific CNN at test time on examples extracted directly from the test image and only from that. And as you'll see shortly, this can often be done quite efficiently. So the first problem we looked at was how we can do by the way, you see this thing at the top here, covering my, my title of the slide? People? Is this covering the title of my slide, or can you see the title of the slide?
We can see the deep internal learning.
So it's not, nothing is covering it. Okay. All right. So we started with super resolution, and just to bring you up to the so that you're on the same page. In super resolution, we have a low resolution image, and the goal is to generate a high resolution image with finer density of pixels. Now, each pixel in the low resolution image is affected by a certain region within the high resolution image. It's a weighted average of several pixels in the high resolution image, what induces a linear relation of convolution and subsampling between the high resolution image and the low resolution one. Now, even if this kernel K is known, this is still it'll pose problems because the number of the unknowns in our high resolution image is larger than the number of knowns, the number of pixels we have in the low resolution image. The problem becomes even more difficult when this kernel is unknown, in which case we call it blind super resolution, because now we have to recover both the kernel and the unknown image. Now, I won't give you an overview of all the super resolution methods. This goes 3 decades ago, but currently the leading methods are by far deep learning based methods, external learning based methods. And their idea is, let's train a network on lots and lots of examples of low resolution, high resolution image pairs. We'll take a network, we'll give it as an input a low resolution image, and it'll have to learn to output the correct high resolution image. And we can give it as many examples as we want, because all we have to do is take a good high quality, high resolution image, downscale it, and poof, we have such a pair of low resolution, high resolution images. So this is very easy. It doesn't require any manual labeling. We can train such networks for days. And then once trained, we can apply it to a new test image that we never saw before. And out comes the super resolved image. And this does amazingly well. In fact, it gave about 2 dB of improvement in PSNR beyond any of the non-deep super resolution methods prior to deep learning. But when we checked, we found out that these wonderful networks work well only under ideal conditions. What I mean by ideal conditions is that first, they have a fixed and ideal downscaling kernel. What do I mean by that? Remember, we generated our low resolution images by downscaling the high resolution images. When we downscale an image, we blur and subsample it with some kernel. Okay. So what do people usually do? They generate the lower resolution images by blurring and subsample with a relatively ideal low pass filter or a bicubic downscaling kernel. But the world is not ideal. When I take a picture of the world, I slightly move my hand. This is not an ideal low pass filter. And you know what? When I'll take another picture, I'll move my hand slightly differently, and it will have a different downscaling kernel. The downscaling kernel is image specific. It's not even camera specific. It's not even photographer specific. Okay, and it varies from image to image. And those networks work really well on bicubically downscaled images. But once you take them out of their comfort zone, they don't perform any better than interpolation. Moreover, they usually assume no artifacts in the low resolution images, but real images have sensor noise, have JPEG artifacts. So as I'll show you shortly, once you take these networks out of their comfort zone, they don't do any better, and sometimes worse than interpolation. More recently, people have started doing blind super resolution in the last year or two. And the idea there is, let's be agnostic to the downscaling kernel. How can we do that? Well, let's downscale the high resolution images with a variety of downscaling kernels and feed them all to the same network. And that way we'll become agnostic to it. So these methods, of course, do much better under unknown downscaling conditions. But still, once you take them out of their comfort zone, out of the type of data they trained on, or out of the type of kernels they assume, they don't perform very well. And I'll show examples. So we said, let's attack this by replacing the external learning with internal learning. And this led us to our first work in this area, which we call zero-shot ZSSR. It's not a new nation ZSSR, it's zero-shot super resolution. Okay, and the idea is, here's our test data. Here's our test image. We never saw anything before in our lives. That's the only image we have. What we're going to do, and we want to super resolve it. What we're going to do is we're going to downscale this image to generate an even lower resolution image. And in a moment, I'll say how we downscale it. And then we're going to train a very light image-specific CNN network such that it will learn how to output back the original low-resolution input image. Once trained on this image, we're going to now apply this network on the input image to generate the super-resolved output image. And the rationale here is that the patches in those two images are the same. There's this strong cross-scale recurrence of patches. So whatever network is good for increasing the resolution of the patches in this low resolution image will also be good for increasing the resolution of this low resolution input image. By the way, can you see my mouse? If I move it, do you see it? Guys?
Yes.
Yes.
We can see it. We can see it.
Definitely.
Okay.
But
So it's the cross-scale recurrence.
wait, just a second. This downscaling, what are the examples you're giving? You're giving the good one and the downscaled one, right?
Yeah, you're saying, I want to teach a network given this low resolution image to generate back this one.
Right, but so you're giving it pairs of
Yes,
of
I get the pairs. Here are the pairs. Okay, I'm training the network to get the downscaled low resolution image and to learn how to generate back the low resolution image.
Mm-hmm.
And then once it's trained on that, I apply it to the low resolution image to generate the high resolution image. Now, we train it on, to further strengthen it, we train it on augmentation generated from the low resolution images by flipping the image, rotating it, downscaling it. This generates hundreds of examples, all generated from the low resolution image, all with the same patch statistics. And this is what gives us this image specific CNN. Okay. Now, what about the downscaling? Remember, I said that the downscaling is image dependent. It varies from image to image. How do we know how to downscale it to maximize this recurrence? Well, it turns out that this can also be estimated directly from the low resolution input image. And so we had an initial work on this in 2013, and more recently we found even a way of computing the correct downscaling kernel from the image using deep learning. And I'll say a few words about this later on down the line, okay? But you can ask, of course, well, how can a CNN be trained at test time? Doesn't it take forever? Well, let's see what kind of information we have internally inside a single image versus externally outside in a general collection of images. Inside in a single image, the patch entropy is very low. Patches repeat themselves. The distribution is quite simple, the distribution of patches. Whereas outside in a general collection of natural images, the patch distribution is very, very high. This means that, and by the way, we showed this empirically in our 2011 paper. This means that internally, I only need a light network to learn how to increase the resolution of this specific image. It doesn't have to know how to increase resolution of other images, just this specific image. In contrast, the external training super resolution, it requires a very heavy network. It has to learn how to increase any patch of any natural image it will ever encounter. It has to memorize how to increase the resolution of all patches that exist out there. So these networks tend to have hundreds of layers, tens of millions of parameters, and take forever to train. Okay, in fact, they usually take days or weeks to train. Our network is a very light one. It's very fast to train. In fact, it takes 8 seconds on a V100 GPU, both to train and to generate the super resolved image. Okay? And this really gives us super resolution in the wild. It allows us to super resolve any data type, any kernel, any scalar aspect ratio. You just tell it all the fly what you want, and this is what you get. So let's look at some results. Here is a low resolution input image with an unknown downscaling. It wasn't bicubically downscaled. It's not an ideal downscaling, but it's a reasonable image. This is what it looks if you just interpolate it. No super resolution yet. Now, this is what happens if you apply one of the state-of-the-art externally trained super resolution algorithms. And if I flicker between the two, you'll barely be able to tell the difference. There is no difference. Now, don't misunderstand me. EDSR Plus is an amazing super resolution algorithm, but it does well on bicubically downscaled images. And once you take it out of its comfort zone, it doesn't do much better than simple interpolation. In contrast, here is the result of the internally trained super resolution without any prior examples. And if I flicker between the two, you'll see the significant difference. And the reason there is such a difference is because we exploit the image-specific degradation, the image-specific downscaling, and the image-specific recurrence of data. Another example, an old photo we downloaded from the internet post-World War II. We have no idea how it was generated. Those of you who recognize it's Checkpoint Charlie prior to building the wall. Here is the result of simple interpolation. Here is the result of one of the EDSR Plus externally trained. Again, flicker between the two. You barely see any difference because this was not bicubically downscaled. And here is the result of the internally trained. And if I flicker between the two, you can see the significant difference. For example, look here at the legs of the man. You can see that we actually recover information which is smaller than a pixel size, which goes beyond the Nyquist limit of the camera or of the image, okay? Or look at this area over here, or the back of the motorbikes, okay? And again, it's because we exploit the image-specific degradation and the image-specific internal recurrence. Here's a JPEG compressed image. Looks okay when it's small, but if you super resolve it with an externally trained network, you get not only high resolution of the signal, but also high resolution of the noise. They cannot tell them apart. Here is the result of the internally trained. Again, if I flicker between the two, you can see that the signal was super resolved, the noise was not. How come? Well, the signals has this nice cross-scale recurrence property. The noise does not. And so the network learns how to super resolve the signal, but it doesn't know what to do with the noise. It doesn't generalize to that. And here's another example with a different type of noise. Again, we don't know what the noise is. The network doesn't know. Here is a speckle noise. Here is the result of the externally trained EDSR Plus, and here is the result of our internally trained. So it's not perfect. We haven't removed all the noise, but again, this was trained to do super resolution, not to do denoising. But again, because the signal recurs across scale and the noise does not, it learns how to generalize for the signal and not for the noise. Of course, we did empirical evaluations. We took hundreds of images. First, we checked we compared ourselves on ideal images. Ideal images being bicubically downscaled images, no noise. Of course, we're not state of the art. The external methods, that's their bread and butter. They do amazingly well on that, but we do reasonably well, nothing to be embarrassed about. But once you take those images out of the comfort zone of those networks to non-ideal images, either non-ideally downscaled or non-ideal noise, okay, then we do 1 or 2 dB better than the state-of-the-art methods without having any prior examples. Now, of course, as I said, you have to know what the kernel is in order to downscale your image, in order to train it. And we said that this downscaling is image specific. How do we go about estimating it? Well, remember, all we have is our low resolution input image, nothing else. We don't know what the high resolution image is, nor the downscaling kernel that relate the two. And we need this kernel because this is what we want to downscale our image with. Okay. It turns out that the correct downscaling kernel, the correct super resolution kernel, is also the kernel that if you downscale the low resolution input image with it, will maximize the similarity of patches across scales in this low resolution image. And this is something we showed in our 2013 paper, and we have an analytic proof of that. And then at that time, in 2013, we solved it we posed this as an optimization problem, and solved using a greedy algorithm. More recently, half a year ago or a year ago, we found a way of computing this kernel also using internal learning on the test image alone. And we call this Kernel GAN. It's a kernel estimation via an internal GAN. And those of you who don't know what the GAN is a short for generative adversarial networks. So I'll explain this in a second. So remember, all we have is our low resolution input image, and we want to find the correct downscaling. We're going to train a network, a generator, which is going to learn how to downscale correctly the image. Okay, what is good downscaling? The one that maximizes the similarity of patches across scale in the image. But we don't have this a downscaled image in order to let the generator train on these input and outputs. All we have is the input for the generator. So how are we going to get the generator to maximize this similarity? Well, we're going to train another network, the discriminator, which is going to get crops sometimes from the generated image and sometimes from the original image. And it's going to have to tell them apart whether they are real or fake. Real, namely, whether they came from the original input distribution of patches in the input image, or whether they're fake, came from the distribution of patches in the downscaled image. And it will generate a map, the discriminator will generate a map that will say whether it believes each and every patch in the image came from the original input distribution of patches or from the generated one. And the generator tries to fool the discriminator to believe that all of these patches are real. And the discriminator trains to resolve the difference between the two. So they both get better and better during training. It's like a police and a criminal, okay? Each one tries to get better than the other. The criminal tries to get away and fool the policeman, and the policeman tries to catch the criminal. So these two networks train together. And once trained, once this converges, this double network thing, this GAN, the generator converges to the correct downscaling super resolution kernel. Now note that this this generator cannot be just any deep neural network, okay? Because a deep neural network is a nonlinear network, okay? It can do lots of things. For example, it can generate a garble of patches or just a collapse to a single patch in the image. The discriminators say, hey, that's great because this patch does exist in the input image. The generator will be happy because it fooled the discriminator, but this is obviously not what we want. What we want is for the generator to satisfy this linear constraint, this convolution and subsampling. Okay. So this is not just any deep linear network. In fact, this constraint is linear, okay? And moreover, it can be realized with a single strided convolution layer, okay? If you look at this, here is the image, here is the kernel, and here is the output of the generator, right? So the generator, all it has to have is a single convolution kernel with strides of 2 if you want to downsample the image by 2, and that's it. And no nonlinearities. So we said, great, let's put this as our generator, a single strided convolution layer. This worked terribly. If these were the original ground truth kernels, then this is what our single-strided generator produced. Horrible results, okay? As you can see, all of these are different downscaling kernels. And as you can see, we got terrible results. And no matter what we did, we couldn't get it to work until, again, Asaf came up with the understanding why it's not working. The reason, as you all know, deep learning works well, it's usually, these networks are usually overdetermined. They're overexpressed, okay? But the reason they converge to a good solution is because there are no bad local minima in deep learning. You have a very complex surface. No matter how you initialize the weights in your network, it'll converge. If you train it, it will converge to a good local minimum if you have enough training data. But this is not the case here. In our case, we have a single good global minimum, the correct kernel K, and no other good local minimum. And so this can never work because if I go back, the generator has a highly non-convex error surface. Remember, it's not only trying to optimize this linear constraint, it's also trying to fool the discriminator. Okay, so its error surface, the loss that it's trying to minimize, is really highly non-convex. And so if we just initialize it with random weights, we'll never converge to the global minimum. We'll get stuck in some local minimum. And so this will never work. But what does work is replacing the generator with a deep linear network. What is a deep linear network? A deep linear network is a deep network with no nonlinearities, no ReLUs or no other nonlinearities whatsoever. And if you multiply all the weights, you get the single desired kernel. So have we gained anything? I mean, isn't this exactly identical? And the answer is no. In the case of the single strided convolution layer, we had a single good global minimum and no other minima, no other good minima. But here, in the deep linear network, we have infinitely many decompositions of this single kernel into different possible weights of the network. For example, if this is a possible set of weights of the network that if you multiply them all give this kernel, then also this would be a good solution for the network. If you multiply one layer with the matrix A and the next layer with the matrix with the inverse of A. And this is true, of course, for any invertible matrix A, and you can do it between any two layers. So you have infinitely many possible solutions, infinitely many decompositions of the weights of the network that will, when you multiply them all, will give you this single kernel. And therefore, we have infinitely many good local minima. And now when we initialize our network with random weights, it converges to a good local minimum. And indeed, if these were the ground truth kernels, and this was the result of a single strided linear, a single strided layer G, this is the result of our deep linear network G. And you can see that the results are very good. This solved the problem. And as far as we know, this is the first practical use of deep linear networks. So far, they've been mostly used by theoreticians in order to analyze networks and understand what they're doing. But as far as we know, this is the first time it's been used practically. And I believe that any linear regression problem subject to nonlinear priors, this is the way to go about solving it, using deep linear networks. So let's look at some results. So here is a real image, again, an old image of John Kennedy. We have no idea how it was generated. Let's look at these two areas. What you see here are the two winners of the blind super resolution challenge in CVPR 2018 in a workshop called Entire 2018. And you can see that they performed quite poorly. Now, they did very well on the data set of the challenge data set of the workshop, but they overfit that data set. Once you take them out of their comfort zone, they don't do very well. What you see here are the result on the right column is the result of our of ZSSR, where the kernel was estimated using Kernel GAN. This is all using internal learning on this single test image. And you can see that the image is quite corrupted, but we can see, look at the pupils that it recovered over here. You cannot see them in any of these images, okay? They look very smooth because that's what they were trained to do, but they don't recover the correct information. What you see here in the third column is the result of our old method, the non-deep method for computing the kernel, when that is fed into ZSSR. And you can see that it still does much better than these methods, but the kernel, the deep internal learning to compute the kernel does better.
Michal, can I ask a question?
Sure.
just about the previous slide. So just to understand, so the difference between the single layer, so this and the deep linear is just that you're doing the same thing. So like your decision functions of going to the next layer are just linear, and yes, instead of something non-linear. But you go several layers. So you do randomization after that again, and so forth. And you're saying that by itself you can prove.
You have infinitely many solutions for this network. For this network, you have a single solution, a single combination of weights that you have to find for the generator in order to be correct. This generator, although the final solution will be the same, has infinitely many solutions. There are infinitely many weight decompositions of this network with the same architecture that if you multiply them all, will give you the same kernel. Okay.
So this is something you prove analytically. It's not sort of obvious.
What?
That's something you prove analytically. It's not obvious.
We don't have an analytic proof of that, actually. Okay, that was an intuition. We don't have an analytic proof that now it will converge. Of course, you have an analytic proof that it will have infinitely many solutions, but it's not necessary. We cannot prove that any initial random choice of weights will necessarily converge to a good local minimum. For that, we don't have a proof. But the fact that you have infinitely many local minima, that is very, I just proved it to you here. Okay, yeah. If this is a good local minimum, then so is this one. If you multiply this layer by the weights of this layer by a matrix A and the weights of this layer by and there are infinitely many such possibilities. And this network has only a single solution. Now you randomly initialize your weights in a network. You don't know how to initialize them. This will never converge. And this turns out to converge. Okay, but we cannot prove the convergence. Okay, we don't have an analytic proof of that. Here's another image. And here you can see the results. And once again, the result with estimating the kernel with Kernel GAN and then putting it into our method did best. We also did empirical evaluations. We outperformed any of the blind and non-blind methods for super resolution, the externally trained by 0.5 to 1 dB. That was true at the time of the submission of our paper. That was a year and a half ago, submitted to NIPS 2019. Since then, many new methods have come out. I'm sure many of them are better than ours, but I'm glad to say that the new challenge winners of NTIRE 2020, which was a month ago, won the challenge, and he is using our Kernel GAN in order to estimate the kernel for each and every new test image. He's externally training the things, but the estimation of the kernel is done using our Kernel GAN. All right, so far, I've only shown you things, how we can use deep internal learning for super resolution. And we saw that this gives us an image-specific CNN. And the nice thing is it's totally unsupervised. It requires nothing but the input image. It adapts itself to the unknown image-specific degradation. And it provides state-of-the-art results on real non-ideal images. But then we asked ourselves, well, can we take it to other domains, to other problems? Can we use it for image segmentation, segmenting an image into a foreground and background layer? Taking an image taken under fog and dehazing it, defogging it, taking transparent, superimposed transparent layers and decomposing it into the individual layers? And the answer is yes. It turns out that all of these tasks can be solved using deep internal learning with no prior examples. In fact, all these three seemingly different tasks can all be solved in a unified manner and put under a single umbrella as a layer decomposition problem and solved with the same algorithm. How come? Well, let's look at this. Each one of those images is actually a linear combination of two different images where the only difference is the mask of weights used to combine those images. So for example, in the case of image segmentation, okay, the two layers are the foreground layer and the background layer. And the combining mask is just the combining weights is just the segmentation mask. In this case, it's a binary mask. In the case of transparent layer separation, here are the two layers, and the combined image is just combined with a constant mixing coefficient mask. And in the case of image dehazing, the two layers are the haze-free image and the fog air light color. Okay, and the mixing coefficients are what's known as transmission map, which is inversely proportional to the depth of scene points and the atmospheric scattering parameters, beta. Now, we don't have to know what they are. All we care about is that this is a linear combination of two images with some mask, okay? And these all can be solved with what we, with an algorithm that we suggested. We call it double dip. In a moment, you'll understand why it's called double dip. It's inspired by work by Ulyanov et al., which is called deep image prior. Their work came out at the same time as our ZSSR paper, the CVPR 2018. And their idea is the following: given a single image, let's train a CNN to output this particular image. So this CNN gets as input noise. The noise doesn't change over time. Okay, it may slightly fluctuate, but it's the same noise of throughout the iteration. And the network has to learn to output this specific image. Now, of course, it won't have any problem. It will eventually overfit this image. But the nice thing is when it does so, during the training process, the weights that the network learn form a deep image prior on this specific image, or in short, we call it dip. Okay. Now, why is this interesting? Well, if you train a dip on a noisy image, then yes, eventually it will overfit this noisy image. But interestingly, somewhere along the way, it generates a clean version of this image. How come? Well, it turns out that the patches in the clean image have much higher recurrence, much lower entropy than in the noisy image. Remember, we said that patches tend to recur inside the image. Well, every patch here will find many other similar patches in the clean image. However, if those two patches were the same in the clean image, they're very different in the noisy image. So the patch distribution is much more complicated in the noisy image than it is in the clean image. And because a deep image prior is a fully convolutional network, it tends to spit out the same things in different parts of the image, okay, because it uses the same kernels in different parts of the image. And so it's much easier for it to generate an image with a simple distribution of patches than an image with a complex distribution of patches. And that's why it locks onto this much earlier than it does onto this. Now, to verify our assumption, we did the following experiment. We took lots of pairs of textures and combined them together to generate a mixed texture. And now, of course, the patch entropy in each one of those texture images is lower than the patch entropy in the mixed image. And now we trained 3 different deep image priors to try to learn each one of those 3 images. And what you see here is how long it took the deep image prior to converge to each one of those images. And you can see that the green curve here, that's the one, how long it took the deep image prior to lock onto the mixed image. It takes it much longer. It is much more difficult for the deep image prior network to learn a mixed image than it is for it to lock onto the orange or blue images, okay? So armed with this observation, we said, okay, we know how to split images into their components using double dip. So here is a mixed image. Let's train 2 deep image priors, hence double dip, so that the sum of these 2 images will form the mixed image, okay? Now, of course, eventually we're trying to fit this network to a single image. Eventually it will overfit this image. But interestingly, when it does so, it tends to split the patches between those 2 deep image priors, okay? And the reason it does so is because it's much easier for each deep image prior to generate a simple distribution of patches than patches that are mixed, that come from a mixed distribution. And to further encourage them to do so, we add an exclusion loss that penalizes for correlation between patches among these 2 reconstructed images. And these form our 2 recovered layers. Now here we use the simple addition. We saw that in some tasks, in some of the tasks, the mask is much more complicated. It's not a simple mixing coefficient. And so we train a 3rd network to learn the mask, okay? And that's the only difference between these different tasks, is the kind of loss we put on the mask, okay? So in the case of transparency separation, we encourage this mask to be a uniform constant. But if we want to train it to do image segmentation, then we request that the mask will be binary. So we give a loss on the mask that it should be binary, and we penalize it if it's not. So for example, for this image, eventually the network locks onto this image. But when it did so, this was the mask it recovered. And here are the 2 layers it recovered. And you can see that one deep image prior learned to spit out zebra patches, and one deep image prior learned to spit out grass patches, because this is the simplest decomposition into 2 simple distribution of patches of the input image, okay? So deep image prior has lots of applications. For example, image segmentation. We took many images, And we applied deep image prior on each input image individually, trained it on each input, double dip on each image individually. And here are the resulting masks that we got, the segmentation masks. Now remember, there is no semantic understand here, no labeling, no manual labeling. And it's of course not going to be as good as semantic segmentation with ground truth data, but it does things that are far from being trivial. It puts those two old ladies in a single layer along with their cards and the background in a separate layer. It puts those three soldiers, by the way, along with their shadows in a single layer. It separates this image into two textures. And it's simply because this is the simplest decomposition into two simplest distribution of patches. We also apply double dip for doing image dehazing. So here are hazy images. Now I want to remind you that a hazy image is a linear combination of the haze-free image and the fog air light, with the mixing mask being the transmission map. So here are the recovered haze-free images, and here are the recovered transmission maps, which are inversely proportional to the depth. And you can see bright here means close, dark means far, and you can see that all of this information was recovered from this single hazy image by training only on that image alone. If you look at this haze-free image over here, you can see that all the grass has more or less the same color. All the hay here is more or less the same color. This is not true for the hazy image. Okay, so the distribution of patches here is simpler, the distribution of colors. Okay, we can use it for transparency separation. This is a real video with transparency. It's not superimposed. It's a real recorded video. Here are the two recovered layers, again, fully unsupervised. And you can see the resulting, this is indoor and this is outdoor. Another form of transparency separation is watermarks. And you can see here that this was the input image. Here is the recovered watermark and the image itself. And I want to remind you that all of this is done with no prior example, simply by training on the input image.
Michal, can I ask you a question? So it's the kind of thing that you would, if we were thinking about the elephants and recordings of one elephant talking over another, and you're trying to separate, that would be in a kind of—
If they would have, look, I didn't try this on audio.
Right.
I don't want to promise, but I would assume that if the spectrograms, I don't know, one elephant over another, I don't know how much their patch, but maybe an older elephant and a younger one, their patch distribution within the spectrogram might be sufficiently different to obtain such a thing. But this would require, of course, adapting this to audio data. Okay. We did it on images.
I'm just trying to think about what is noise in the setting of sound.
And it's not perfect. You know, there are many cases where it would split things into things that you wouldn't necessarily want. It just looks for the simplest split into the distribution of patches. So there seems to be something really strong about this distribution of patches. It's like a fingerprint of an image. And we want to say, can we somehow capture this gist of an image? Can we take an image and generate other images of different sizes and aspect ratio that have this same DNA, this same patch distribution as the input image? Or in other words, we want to capture and retarget the DNA of an image to generate lots of other siblings with the same patch distribution. And it turns out, once again, that this can be done via an internal GAN. So once again, we train a generator, okay, to generate these new images with the same patch distribution. Okay, so our generator, G, is going to get random sizes at each training iteration, and it's going to output images according to those random sizes that we sample. Now, initially, they're not going to look very good. They're going to be garbage. How can we guarantee that they come from the same patch distribution? Well, we're going to feed crops from this image and from the original input image into a discriminator that will try to tell them apart. It will try to say which ones came from the real distribution of patches in the input image and which ones came from the generated distribution of patches. And again, it will generate a map saying where it believes things came from the original input image and where things came from the generated distribution. And of course, the generator will use this mask to learn how to improve, because it wants the discriminator to think that everything came from the input distribution, and the discriminator will try to get better. Think whenever something is fed to it from the generator, it will try to say that everything is false, and whenever something is fed from the input, it will try to say that everything is true. This is very easy. When we feed those crops, we know which ones we gave him, the discriminator, so we know the ground truth label, false or true, okay? And once they converge, the generator now becomes a network that if you feed the input image into it in any random size, it will generate an output image of this random size with the same patch distribution as the input image. So here, for example, by the way, there's much more sophistication to this, but I have no time to go into details. So here's the input image. We asked a smaller image. This is of a certain size. This is what it gave us. You can see that it's stripped off windows. It's stripped off rows of windows. It's stripped off bars here from the barn and the back here. But all in all, locally, everything seems as if it has come from the original patch distribution. The discriminator has a small field of view. It cannot tell them apart. Here is a large image, and you can see that it added many rows of windows and many windows in each row. It added many more sticks here to the barn. But again, locally, everything seems valid to the discriminator. Here is an image with a different aspect ratio, but it doesn't change the aspect ratio of the elements inside the image. It doesn't grow them or shrink them. It just multiplies them. And of course, we can do it for any range of scales. For example, here's an input image. We can now generate, and unfortunately, my screen is jumping, which is really making me mad because this is supposed to be a smooth video, and it looks horrible. But if you look on my website, you'll see that this smoothly goes. You see that it doesn't, it shouldn't go like this. I don't know. Anyway, sorry about this. This is my office PC and the screen is terrible. But you see that the fruits don't grow larger or smaller. It just gives birth to more fruits, to more boxes of fruits. You can see that as it grows up, it adds rows of watermelons and so on. And we can also do this for any other types of deformations, affine deformations and so on. You can see that still the patch distribution remains the same. It doesn't distort the elements inside the image. We can take a building, add windows to it, add rows of windows, floors, stories. Everything is done using the same trained generator on the single image. We can add columns to the building, or we can take this penguin, and you can see the penguins don't grow any fatter. It's just the penguin gives birth to new penguins, okay? And all generated by training on the single input image. Of course, no one's perfect. Our generator has no notion of semantic understanding of objects or scenes. It just tries to preserve the patch distribution at multiple scales. And therefore, it would generate these kind of images. Locally, everything looks fine to the discriminator, but globally, it looks funny. By the way, if we were to increase this, to further stretch this image, it would split it into two people. This is also what happens in the penguins. At some point, you'll get a penguin with two heads, and then it would split into two penguins. There's no way of avoiding this. Here, I want to show you something totally new, what I call mind reading, how we can decode images, recover back images from brain activity. This is work that appeared in Neurops half a year ago. And since we published it there, we had a leap improvement in results together with Niv Granot. And this is what I'll show you here. So we hope to publish this soon in a journal, this extended version. But the idea is the following. You have a person lying in an fMRI machine, watching images, and the brain activity is being recorded. And we look at the area of the visual cortex. And the question is, can you recover, can you synthesize back the input image from those readings in the visual cortex? Not only can you reconstruct it, can you also classify the image? Say that this is a cheetah, I don't know, okay? Just from looking at the visual cortex. Now, this is of course not a new problem. People have been looking at this over more than a decade. It started with the amazing work of Jack Gallant and Kay and Naselaris and Kamitani, and I'm not a neuroscientist. They have an amazing set of work. And the idea is, given pairs of images and their fMRI recordings, try to train a decoder, okay, to take the fMRIs and decode it into images, train it on those images, and then try to apply it to new fMRI. And initially, those methods try to do this using linear regression between fMRI and images. And more recently, people have started doing this using deep learning methods. But the problem shared by all these methods is there is simply insufficient training data. These data sets, and we use existing data sets, we don't record fMRI by ourselves, typically have 1,000, 2,000 image and fMRI pairs of data. That's far from being sufficient to cover the space of all natural images, and you want to be able to recover a new image from an fMRI of a never before seen image. It's not like you can put a person that long in an fMRI machine, so you can't record too many images. And it's not like you can record images, show one person those images and record as fMRI and show more other images to another person, because these fMRIs differ from brain to brain. And also the signal to noise ratio is terrible. Every voxel in the fMRI covers 100,000 neurons, averages information over several seconds. That's the shitty data we have, okay? And that's what people have been using, and that's what we've also been using. But we said, hey, let's add self-supervision to this. And the idea is the following. On one hand, we have those 1,200 supervised examples. Great, we're going to use them. We're going to train two types of networks: a decoder that will learn how to decode fMRIs into images, and an encoder that will learn how to encode images into fMRIs. So initially, we'll train them on those 1,200 images. Of course, they'll do great on those 1,200 images and on those 1,200 fMRIs, but they will not generalize well to new images or to new fMRIs. But here's where the trick comes in. Here's where the self-supervision comes. We're going to take those two networks and stick them back to back. Now, this combined network, its input is an image. Its output is also an image. So if trained well, then given any image, it should be able to output the same image, even though this image, we may have never recorded any fMRI for it, okay? Given that we don't need fMRI, we can train it on as many images as we want. Tens of thousands of ImageNet images, okay? From completely different statistics than one the person saw in the fMRI machine. And we're not gonna only ask that the images will look the same, but we're also gonna ask that the semantic features extracted from those images on either side will be very similar, okay? And that will guarantee that we semantically recover meaningful information, including new classes and so on that were never viewed in the fMRI. But we will do more than that. We flip the order of those two networks. Now the input is an fMRI signal and the output is an fMRI signal. And we can train them on fMRIs without knowing what the paired images are at all. In particular, we can train them on the test fMRI itself, the test fMRI that we wish to decode. If trained well, the output should be equal to the input. Okay. So in our network, we train those two networks, the decoder and encoder, using all these four losses. Okay, both training data, supervised information, as well as self-supervised information in both directions. And by the way, training on the test fMRI gave us a huge leap because it adapts itself to the statistics of the new test data. So let's look at results. What you see here are the 50 test images in the dataset that we use, no cherry picking. Here you see a pair. Left is the original image the person saw, right is the image we recovered from the fMRI readings. Okay, so here's a fish. Here you can see a llama, an airplane. This is some outdoor scene. This is the cheetah. Here's a boat or whatever, canoe, a beer cup, a fly, yeah, or this ski, the snow bike, whatever it is. And of course, we also get bad results. Okay, here you cannot recognize anything, I dare say. And sometimes the colors are off. So there's still a lot of place for improvement. But we're really excited about this, and we believe that we can do much more. I don't know if I have any time left. I have one last thing to show, but yeah, but will we have time for questions afterwards? This will take me 5 more minutes. What's the decision, Shafi? Should I skip this or should I show this?
Michael's in charge, really.
I didn't hear.
Please show, and in the worst case, we'll compress the questions.
Okay. All right. So here we tried extending the idea of deep internal learning to video. So far, I showed you everything on images. And once again, the first problem we started looking at is, can we use this for temporal super resolution, zero-shot temporal super resolution? And this is an upcoming paper at ECCV 2 weeks from now. And the idea is the following. In spatial super resolution, we want to increase the pixel density in the image. In temporal super resolution, we want to take a low frame rate video and increase the frame rate. Take a 25 frame per second video and generate a 200 frame per second video from it. But we don't want to just interpolate. We want to recover dynamic events that occur faster than frame rate and therefore are invisible in the original input video, that go beyond the temporal Nyquist limit of the input video. For example, you would want to be able to undo motion blur and motion aliasing. Here's an example of motion aliasing. This fan is rotating clockwise faster and faster. But at some point, because it's rotating so fast, it appears to be rotating counterclockwise. And this is simply because we're sampling it at 25 frames per second. That's not enough for the temporal frequencies here. And also you see a lot of motion blur from the moment the shutter opens until it closes. The fan moved a lot, generating this blur. Note that interpolating in time will not help resolve this problem. It will not undo motion aliasing nor motion blur. Temporal interpolation, no matter how sophisticated it is, cannot undo these effects. In super resolution, in temporal super resolution, we want to be able to resolve both of these effects. And we extend this idea of zero-shot super resolution from images to space-time, and you can find many details in our paper. But there are two very sophisticated augmentations that we use in this case. Okay, one augmentation is generated by blurring and subsampling the video in time. Okay, what it does is it simulates. So if this was the video in the original, now note that the frames have not changed. If this is the video in the original temporal resolution, then this is the video in the coarser temporal resolution. It's got more blur, it moves faster. And at some temporal scale, it will already have motion aliasing, okay? So going deeper in temporal scales synthesizes higher speed, more motion blur, more motion aliasing from the input video. We can now take these pairs of videos and train a deep network to learn how to undo these effects, these video-specific motion blurs and motion aliasing. And once trained, we can apply it to the input video to generate the output video. Another very sophisticated augmentation that you can apply to the input video, and this is based on a totally new observations of ours, that patches recur not only across different scales of the input image or input video, but in the case of video, also across dimensions of the video. What I mean by that is if you have a space-time volume, XYT of the video, okay, and then the spatial slices of the space-time volume generate our video frames. But if you now take this space-time volume and rotate it so that one of the spatial axes becomes the temporal axis and now slice it, then now you get space-time slices of the video. Now look at them. You can see the cheetah here. They look quite similar to the original video frames, but they have aliasing in time, okay, because they weren't sampled fast enough in time. However, there's a lot of similarity. There's a lot of recurrence across scales between the original video frames and those temporal slices, and therefore we can use the high resolution examples from the original video frames in order to undo the temporal aliasing in the temporal slices. And you can find many more results, the examples in our paper and explanations, but let me just show you results of temporal super resolution by a factor of 8. So here is the input video you saw before. Here is our result. What you see here is NVIDIA slow-mo, Dane, and flawless. These are different ways of interpolating in time or super resolving in time videos that are, these are externally trained. Ours is internally trained. You can see that they cannot handle motion blur nor motion aliasing. Here is another example. This is the input. This is our output. This is, by the way, the ground truth high resolution. We generated the input from it, and by blurring and subsampling in time. And here you can see the competitors, and you can see that we do better. Of course, it doesn't have to be repetitive motion. These are diamonds falling. Here is the input. Here is our output. And you can find many more examples on our website, including complex videos like splashing water, flickering fire, and other things. So to summarize, I hope I've convinced you that there's a lot of recurrence of information inside visual data. And this gives rise to internal learning, generated image-specific CNNs. It combines the power of deep learning with internal image-specific or video-specific priors. It is totally unsupervised. It needs nothing but the input image. It adapts to the unknown image conditions and degradations. It gives state-of-the-art super resolution results on non-ideal images, but it can also be used for dehazing, segmentation, transparency separation, retargeting, and so on in an unsupervised way. What's next? Can we use it for high-level vision tasks, video analysis beyond super resolution? Can we combine the power of internal learning and external? Right now, we train a network from scratch for every new datum. Can we use prior knowledge on externally provided examples and only fine-tune it, but it's not going to be regular fine-tuning on the new data? And there are initial papers showing, not by us, but by other people, showing the power of this combination. Can we apply it to other type of signals, audio, non-human communication? I believe so, but it requires the proper adaptation. And I'd like to give credit to all the people who worked with me, Asaf Shocher, Yossi Gandelman, Sefi Belkligler, Shai Bagon, and Philip Izola, and primarily Asaf Shocher, who is the main driving force behind all the deep internal learning stuff. In the case of the fMRI work, the people responsible for this are Roman Bailey, Guy Gaziv, Niv Granot, Asaf Hugi, Tal Gulan, and Francesca Starpini. And in the video temporal super resolution, it's work by Liad Polak, Eyal Naor, George Pisha, Shai Bagon. And thank you for your attention, and I hope I didn't take too much time. Where signal to noise can be very low. It's a good question. I'm now starting to look at these things together with people from biology at Weizmann. I don't know yet. I will be smarter in a year or so, but we are looking into this. Yes. I have a few questions, if I may. One, is it safe to say internal learning, single image equals external learning across patches using symmetries, invariances, and scale-free properties? I'm not sure I understood. It's not the same. I mean, let me oh, maybe I'll read the question all the way to the end. Maybe I'll understand it. Will this only work for downscaling that is symmetry preserving, such as linear translation, invariant downsamplers? There's a striking similarity with max entropy methods in image processing, say with wavelets. Is the scale-free property enforced through such a criteria? First of all, the downscaling we do is very similar to wavelets. Okay, this is regular Gaussian pyramid, but wavelets are just different types of pyramids. So I believe that there can be the proper recurrence in those cases. Okay, and it doesn't have to be only downscaling. We also found recurrences across rotations and things like that. There are many geometric transformations that will preserve this patch recurrence. And if you look at our 2011 paper, which analyzes the internal statistics of a single natural image, it looks at other types of transformation. As I said, scaling, also flips are, and also rotations, and there may be others. Also, you don't necessarily have to scale the same way. If you have an edge, let's say if you scale only vertically, then you'd still have the recurrence, even though you haven't scaled horizontally, or you can. So I believe that it's much more than just what the kind of recurrences we used. Whether internal learning on a single image is equal to external learning across patches, I'm not sure I understand the question. Maybe one of the panelists understand the question, but as I said, each image has its own image-specific degradation, for example, in super resolution. You can't train a single network to handle all these degradations. If it will, and also your data for training may be different than maybe you trained on natural images, but now you want to apply it to medical images. That's different data. It's not going to be the same network. In the internal learning, the advantage is that the data you train on is the data you want to apply it on. Okay, that's the advantage. But it's got its disadvantages. Of course, if you have lots of external training data, it's extremely useful. It will, and if it's good training data, it'll be more powerful than simple internal learning on a limited amount of data. So this is not to replace, it's to augment the information that what we know to do, but when there's only very little data to train on. And the third question, are there any examples of incorrect image decompositions? How frequently do they crop up? Oh, of course, we have lots of examples of incorrect decompositions. We're not claiming that, by the way, the dehazing decomposition were actually comparable to state-of-the-art image dehazing methods that were trained with external examples uniquely for this purpose. We do comparably well. Image dehazing, it does amazingly well. For the image segmentation, it's nowhere near semantic segmentation, okay? It does what it does. Sometimes it makes sense and sometimes it doesn't. It just tries to find the decomposition into two simple distribution of patches, but these may not necessarily be the decomposition that you want. For example, if you have a horse and the background scene, and the background scene has houses and trees and grass and people and kids and dogs and I don't know what. It won't necessarily, maybe there's a dog with the same color of the, or similar texture to that of the horse, it will probably put them together in the same layer. It's not necessarily semantically meaningful, okay? So I think I answered all the questions in the Q&A.
Thanks a lot, Michal. So again, a wonderful talk and very inspiring and great results as usual. I think, well, no surprise that you really had this legendary reputation of getting publications into any computer vision conference. So thanks again for joining and presenting.